Welcome to Grade 11 Artificial Intelligence. You have trained models before in a notebook on your own machine. In this module, we ask the next question: how does that model become a real service that thousands of people can rely on day after day? That craft has a name, MLOps, and it is what turns an experiment into a product. Here is our plan for the module. We'll see why a notebook model is not yet a product. We'll walk the machine learning life cycle from end to end. We'll version data, model, and code together and set up continuous integration and delivery. Then we'll serve the model to users, package it in a container with Docker, and finally monitor and scale it in production. Let's begin where you already are, a notebook that trains a model and prints a good score. That is real progress, but it is the start of the job, not the end. A notebook runs once for you on the data you already have. Production is different. It must run every day for many users at the same time on data the model has never seen. And here is the lesson that surprises most beginners. The trained model is a small part of a much larger system. Most production failures come not from the model itself, but from the pipelines, the data, and the plumbing around it. To manage all of that, we follow a life cycle. A model in production moves through 4 stages over and over. First, data. We collect it, clean it, and label it. Second, train. We fit a model and evaluate it honestly. Third, deploy. We serve that model so real users can reach it. Fourth, monitor. We watch how it behaves in the wild. And this is a loop, not a straight line. The world keeps changing, so fresh data flows back to the start, the model is retrained, and we redeploy. To run that loop safely, we first need to keep track of exactly what we are changing. That brings us to versioning. In ordinary programming, we version the code. We use Git to record every change, so we can always go back. In machine learning, the code is only one of 3 things that decide the result. We must also version the data, the exact data set that trained the model, and the model itself, the trained weights, tagged and stored so we can fetch that exact version again. Why does this matter? Because a single prediction is the result of this code on this data with this trained model. Change anyone, and the answer can change. Pinning all 3 is what lets a teammate reproduce your result and lets you roll back safely when something breaks. Once everything is versioned, we can automate the path to production. Continuous integration and continuous delivery automate the path from a change to a deployed model. Continuous integration means that every time someone changes the code, an automated system tests it at once. In machine learning, those tests check more than the code. They check the data is valid and that the new model still meets its accuracy bar. Continuous delivery means that when the tests pass, the build can ship to production automatically. The whole point is to catch problems early and to release small changes often, rather than one large risky update once a year. Now the model is built and tested. How do users actually reach it? Serving is how a model is exposed so other programs can ask it questions. There are 2 common styles. Online serving answers one request at a time, quickly. When a mobile money app needs to flag a single suspicious transaction right now, it calls the model and waits for an answer. Batch serving is the opposite. It scores millions of rows at once, on a schedule, say every night. In both cases, the model sits behind an endpoint, much like a web address. An application sends its input to that endpoint and gets a prediction back, often in a few milliseconds. But to run reliably anywhere, the model needs to carry its whole environment with it. Every engineer has heard the phrase, "It works on my machine." The model runs on your laptop, then fails on the server because the libraries and settings are different. A container solves this. A container image bundles the code, the exact libraries, and the settings into one sealed package. Docker is the tool that builds these images and runs them the same way everywhere. Because the package is complete, the very same image runs identically on a server in Kigali, a laptop in London, or in the cloud. No more surprises from a missing library. With the model packaged and served, we must keep watching it once real users arrive. A deployed model needs watching because it can decay quietly while the code never changes at all. We monitor two things. First, system health, how fast it responds, how often it errors, and whether it stays up. Second, model quality. Is it still accurate when we check it against fresh labeled data? The quiet danger is data drift. The world the model serves slowly changes. New shopping habits, new crops, new fraud patterns, so the incoming data drifts away from what the model learned. When monitoring detects that drift, it triggers a retrain, and we are back at the start of the life cycle loop. The last question is what happens when not hundreds, but millions of users arrive. Scaling is how we keep the service fast as demand grows. There are two ways to scale. Vertical scaling means moving to a bigger, more powerful machine. That helps, but a single machine has a ceiling. Horizontal scaling means running many copies of the container side by side, sharing the work. A load balancer sits in front and spreads incoming requests evenly across those copies. Best of all is autoscaling. The system adds more copies automatically when traffic spikes and removes them when things go quiet, so we only pay for what we use. Tools like Kubernetes do exactly this orchestration for us. Let's see how all of this looks in the real world. These ideas are already running behind everyday services. In Rwanda, a fraud detection model can sit behind a platform like Irembo, retrained as fraud patterns shift over time. Across Kenya and India, crop advice models are served straight to farmers' phones, scaling up during the planting season. In the United Kingdom, a hospital triage model is monitored carefully for drift and for fairness across patient groups. And in the United States, a streaming service's recommender autoscales every evening, adding copies for the peak and removing them late at night. Different services, the very same life cycle underneath. A few traps catch almost every team, so let's name them. First, thinking the model is the whole system. It is the smallest part. The surrounding plumbing is the real work. Second, versioning the code but forgetting the data and the model, so the result can never be reproduced. Third, deploying once and then never monitoring, so drift goes unnoticed until users complain. And fourth, having no rollback plan, so a bad new model cannot be reversed quickly. Avoid these four, and your service stays trustworthy. Let's gather the key ideas. A notebook model is not yet a product. The life cycle is a loop: data, train, deploy, monitor, and round again. To reproduce a result, version the data, the model, and the code together. Continuous integration and delivery automate and test the path to production. Containers, built with Docker, make the model run the same everywhere. And in production, we monitor for drift and scale with load balancing and auto scaling. Now let's check your understanding with 3 quick questions. Here is the first question. A model worked perfectly on your laptop, but it crashes on the server with a missing library error. What tool packages it to run identically everywhere? The fix is to bundle the code, the libraries, and the settings into one sealed package. That package is a container built with Docker. Question 2. A deployed model's code never changed, yet its accuracy on fresh data is falling month after month. What is the most likely cause? The code is fine. The world has moved. The incoming data is slowly changing shape. This is data drift, and the answer is to retrain the model. Last question, and it brings several ideas together. A mobile money service in Kigali sees traffic spike at lunchtime and fall overnight. What scaling approach keeps it fast without overpaying off-peak? We want more copies at the busy time and fewer when it is quiet. That is horizontal auto-scaling with a load balancer spreading the requests across the copies. Excellent work. You now understand MLOps, the lifecycle loop, versioning data, model and code, continuous integration and delivery, serving, containers, monitoring, and scaling. You can take a model from a notebook to a service that real people depend on. In the next module, we turn from how we build AI to how we should build it, and explore AI ethics and governance frameworks. I'll see you there.